Hello everyone, welcome to 590 seminar. Today Nova and Peter is going to present. Nova is an undergrad student working with Professor Haran, senior.
Yeah, senior.
And Peter is a graduate student and also working with Professor Haran. And they are going to talk about conceptual design of an eVTOL as shuttle for rapid intercity transport. We are going to fly Chicago in.
That's right. Thanks, Stepan. Okay, so as Stepan said, Peter and I will be talking about an RSO that we started earlier this semester. And it's also like a research platform for Professor Haran's research group to develop some key enabling technologies. So to give some context, and now it's not working. Okay, so to give some context, you may have received an email earlier this semester about UI Ride. It's basically a shuttle bus service from Champaign to Chicago and also to Springfield. And so it's meant for encouraging collaboration between the universities and providing a more comfortable and productive transit between the different universities. So the whole idea is just that, to make it more comfortable, but it doesn't really solve the problem of a long transit time. And it kind of just cures the symptoms. So as we move forward, we're going to be basing our entire design and comparing it against UI Ride. So it's important to know a couple of the offerings of UI Ride. And that is that it offers 18 passenger capacity. It has restrooms, workstations for working during the transit. It also has Wi-Fi and a concession kitchen. And you can also, each person can have one carry-on bag. So, and all of that for a grand total of $40 to $50 per person. But that's billed to the university because general population can't use this service. It's only for faculty and students on official university business. So what's the solution to the problem, right? Well, we believe it's a VTOL aircraft. And because we're electrical engineers and we believe in a sustainable future, we'll put an E in front of it, right? And so you may have seen a couple of different companies doing something similar. So like Lilium is a big one, Ehang from China. And the idea is similar, right? So it's obviously VTOL stands for vertical takeoff and landing vehicle. And so the idea is to maneuver around in an urban environment and land directly where you want to land. Some of these aircraft also transition to horizontal flight so that they can have a more efficient cruising. So obviously it has a small profile for maneuvering in urban environments, and the whole idea is you have multiple layers in the air, and you're not really delayed by, there's no traffic, right? Like the transit times from Chicago to Champaign is about 3 hours, right? So, and that's kind of not unique to just Chicago to Champaign. Kind of like the 200 to 300 mile range is tough for transportation-wise. So you could take a bus, a car, a shuttle, train, plane. It's all going to take you around 3 hours, including checking in and everything. So there needs to be this new form of transportation, right? And so this is one idea. The problem with all of these is that they only can hold about 1 to 2 people. So it's not really economically feasible. Because, I mean, if you imagine like an Uber driver can barely make profit because the overhead of owning a car and the gas, it's not really profitable. So imagine if they had to buy a flying aircraft, it's a little more overhead for that. So the idea is to scale it up. So that's our whole concept is adding 10 person, right? And hopefully 200 miles, up to 200 miles range. And we'll transition to horizontal flight similar to Lilium. And we'll do that by extracting the most out of our propulsion and also our energy storage elements. So obviously specific power increases. Like I mentioned earlier, Professor Haran's group is using this as a test bed for their developing technologies. And so they'll provide some key insight into increasing the specific power of machines. And also we'll do a co-design, so of a propeller and a motor pair, and hopefully a short-term overload. So designing for a cruise, and then so you can lower the weight of your motors and short thermal bursts. So you have to handle the cooling for that necessarily. So why is now the right time? Well, there's a lot of financial backing. So you can see over here some of the funding going on between Lilium, EHang, Joby Aviation. There's millions of dollars being put into this. And down here you can see NASA's 10-year funding plan. So there's billions of dollars into what they call New Aviation Horizons, which is electric flight and electric VTOLs. X-57 is part of this funding plan. So over here you can see NASA's greased lightning concept, which is basically just demonstrating the transition between vertical and horizontal flight. And so that's what we're kind of basing off of. It's a subscale model. So this is kind of a predecessor to X-57, even though it doesn't transition similar. Also, there's been some key developments in technology. So the energy density and and power density of fuel cells has increased over time. You can kind of see here, this is the 1-hour discharge time. So around here is our current technology, and there's small trade-offs between lithium-ion batteries and current fuel cells. And then we also include fuel cells with liquid hydrogen storage. So the technology is increasing. This is projected fuel cell with liquid hydrogen storage in the near future. And so hopefully we can surpass jet fuel. Also over here is kind of the state-of-the-art of specific power in electric machines. Around, you can see these are kilowatt range, so it's around 5 kilowatt per kilogram. And so, Professor Heron's group is working on a 13 kilowatt per kilogram, 1 megawatt motor. So the technology is increasing. And as well, there's been some aerodynamic research on boundary layer ingestion and distributed propulsion, how electrification can help those aerodynamics. There's also supporting government regulations. So the FAA is working on their own regulations. The European Union Aviation Safety Agency also published their own specifically for VTOL. So there's some support, and obviously there's a social need. So as I mentioned earlier, there's this gap in transportation. So it's kind of necessary, especially as people move out of the cities, and there needs to be a more efficient form of transportation between the rural areas and the urban areas. So how are we getting there? Well, this is kind of a projection of how, if we increase the state-of-the-art of energy density and power density of our propulsion, then we can get to where we need to be for our specific design. And these aren't real numbers, but this is just how we believe it should look in the range versus payload. We're also working on creating an optimization scheme for developing the parameters for this vehicle. So that entails a genetic algorithm-based optimization, and we can vary a bunch of variables like structural dimensions, propeller efficiency, pitch, rotational speed, and including the mission profile. And so we can vary all of these and get out a fitness function, evaluate it, and generate the next group of parameters. And from that, we can kind of, hopefully it'll point us towards the right direction for the specific parameters of our vehicle. But for now, we're kind of going off of preliminary first pass evaluation and not optimized. As I was talking about earlier, we can design for cruise. So you can imagine taking off, getting the most out of your machine. So that means going over rated power. And so that way we can size the machine for cruise, which is very efficient. But during takeoff is the maximum power point. So if we can just for a short amount of time, just overload the machine, which requires some pretty significant cooling methods, then we can overcome and design lower weight. And also increasing the efficiency with co-design. So Peter's going to talk a little bit about that. Do you want this?
Thank you. Hello. Okay, so the electric motor and the blade, the propeller, are the key components of the electrical aircraft. It's not only for Atlanta Air Shuttle, but also for Cheetah program. Me and Ranbir are working on optimization of this pair. Why is that important? Because those are the key power source. The electric power the electric motor can convert electric power to mechanical power, and the propeller convert mechanical power to actual work that propel the aircraft. So those two are the main source for this aircraft to take off and to fly. So that's why we want to optimize this pair. But why this pair is so important? Because those two likes different thing. For motor, so first let's look at the trade-off. I have the picture here showing two different type of composition of propeller and motor pair. On the left is a big electric motor and the same size of a propeller. On the right is a smaller motor of the same size propeller. So we call the size of the motor the hub size. So if you increase the motor, there will be a certain amount of air in the middle of the propeller being blocked. Where the motor stays, take the location, the air cannot flow through, which reduce the amount of thrust you can generate at a given RPM. So according to the equation or the relationship here, the motor likes bigger diameter. The bigger the diameter, it can be more efficient. But propeller, if you have a too big motor, it blocks almost all the air through the propeller. It's not going to work well for the propeller. So this conflict actually creates the trade-off that we want to study. What is actually the best hub to tip ratio that we can optimize the performance of the motor and propeller pair? During a preliminary study, we find some characteristic of the propulsive force generated by a propeller. This is a typical two-blade carbon fiber propeller. Based on that, there's a curve. This curve shows the hub effect on the total thrust given a propeller. It's a simple relationship calculated using blade element theory. So the x-axis is a hub to tip ratio, which is how much this hub takes the space of the entire propeller. If there's no hub, everything is blade, it's 0. If there's only a hub, no blade, that is 100%. The y-axis is the thrust to is basically a normalized thrust. Is the ratio of the thrust over the maximum thrust it can generate at a given RPM, which is all of them is blade, no hub. So as you can see, if you increase the hub a little bit to about 30%, you can still get a 95% thrust out of the same propeller. It's only when you increase to 50, 60%, there's a significant drop that prevent you from further increase the hub, because if you just spin a cylinder, there's no thrust going to be generated. So this one actually boosts our confidence that we can actually find a point where we can find the most efficiency point of the blade and the motor pair, considering both the efficiency of the motor and the propeller. So next, I'll briefly introduce the overall parameters of this multi-copter, the Elina Air Shuttle. So to begin with, I'll state our general configuration. We have 2 pair of wings with 10 motors with propellers on it. So those 2 wings are rotatable. They can, as you can see from the previous 3D illustrated graphs, it can rotate. During takeoff, it rotates 90 degrees, and then you have the propeller shooting air downward, take off vertically and landing vertically. And during cruise, it shifts to the horizontal position so that it can cruise efficiently, because aircraft using wing to cruise is probably the most efficient way you can go through in the air at high speed. And also, it's small. This is a Tesla Model S. And it is pretty small. It's like 2 Teslas, and it's probably almost the same size as a bus that takes 10 people. So we hope to have it take off and land in a normal parking lot. So I think this small profile will allow us to do it. And also for the assumptions that we made for electrical system, we made very achievable electrical parameters. For instance, the motor specific power, the power electronic specific power, and the battery electrical specific energy. Those three are supposed to be achievable in probably 20 or 30 years. And with that, we derive this table using some first order equations so that we have the fundamental concept of what it will look like, how much power it will draw, and how heavy it might be. With that, we go to it's a mission profile because we need to know what mission we're going to accomplish in order to design our aircraft. This is actually the step that we take before we design the actual aircraft. So above is a graph showing the altitude versus the time probably the spent in the air, and below is a table showing the duration of each segment, and then the power is also a normalized power associated with each segment. As you can see, we expect people, after spinning the propeller, we probably spend a minute on the ground before we're lifting up. Probably take 2 minutes to reach a reasonable altitude to clear all the tall buildings so that we can transit to a horizontal flight. And we climb horizontally so that we can maximize our efficiency, and we cruise for most part of to cover most part of our range. And then we start to descend probably 20 minutes before we reach the destination so that we can make use of those altitude that we have achieved. Otherwise, we just land, cover those altitude. Those altitude are not useful for us. For in this way, we use 20 minutes to glide down so that we make use of those potential energy that we gain in the initial ascent. And then we plan 5-minute loiter to see what's going on the ground, if it's practical to land. And then if anything happens, we can divert. We prepare a 15 minutes divert time for this mission. And then approaching and landing and shut off everything, we plan for 3 minutes. So overall, this mission, I refer 2 types of aircraft for this mission. One is the regional jet. Has very similar mission profile as this, and also the helicopter has very similar to mission profile as our aircraft.
Yeah. So to encourage some first pass safety analysis, we are working with Professor Sayan Mitra over at CSL on, they have a safety verification software that runs on power system models. So we're developing a Simulink model. So this is one cell, a motor controller, a motor, and a load profile that we used. And once we finish this and the overall power system, we'll hand it over to their team and they can run some safety analysis on it. So to do this, I did a first pass motor design in MotorCAD to get the parameters, and we input that into the machine. And then also we extracted the torque speed curve of a typical propeller that provides the right amount of thrust for us, and we applied that as a mechanical torque to the machine in Simulink model. And so over here you can kind of see the one type of power system that we could use, and the key here is redundancy, right? So if something fails, it can't cost human lives. So we have some redundancy in that if a DC to DC converter fails, that we can reroute the power from somewhere else and apply it to the motors. Or, for example, if one of the motors fails, we can choose, or if one of the inverter fails, we can choose which one to power, which motor to shut down. So Peter and I did a preliminary failure mode analysis, and we kind of chose that, we decided that this specific power system might not work. It might not be feasible. So we're working on developing different types of power systems that might be more feasible. And in the future, we hope to do a couple of thrust tests on propellers. We're sending out a 3D model to get printed, and then we can put it in a wind tunnel and get some aerodynamic data from that, as well as we want to complete the optimization that I was talking about earlier. And we have a video here of running one of these motors, a 5 kilowatt motor, but I'm not sure if it'll play. But something similar to this, right? So just have a motor, propeller, and then we'll have some thrust measurement system, and we'll get some useful data on how efficient the propeller is and how much thrust we can get out of one motor. So with that, the last thing I wanted to mention is that we have an RSO, and it's called Illini Air Shuttle, or IAS. So if you're interested in joining, we could always use upperclassmen or graduate students and their knowledge. So please come to me and let me know, and we can find something for you to do in the club. Any questions?
So are you guys planning to build like another full prototype of aircraft, or just like demonstrate new technologies?
In the far future, so the club is specifically meant for undergrads to kind of start working on this type of technology and get their hands and do actual work. But I mean, this type of technology is far in the future. I mean, at least 10 years, right? So in the short term, we can start to develop some subscale models and do some testing on that. And that's also part of the research.
Do you have any rough numbers on what the cost per passenger would be for
We're not at that stage yet, but the whole idea, if it's unaffordable, then we're not really doing anything important, right? The idea is for it to be used in mass setups. So if we want to compare it to the UI ride, I mean, $40 to $50 seems like very, I guess, a tight constraint, but hopefully we can achieve that. But yeah, if it comes out to be $500 per flight, then it's not worth it.
So what's the trade-off between putting 2 motors versus 10, 12 motors?
Yeah, so that's an aerodynamic perspective. So it depends on your propeller sizes and your efficiencies of your motors. So that's all going to be put into the algorithm, the optimization algorithm. So
have you guys done so far any study, or it's a kind of study in progress?
It's a study in progress for sure, because I could imagine that if you have more motors, and your efficiency of each motor is going to be less, because you have to run them at higher speeds to get the same amount of thrust. And that speed, so basically these propellers are better suited for, larger propellers are better suited for more thrust at lower speeds. So we can, it's hard to exactly say, but we can definitely optimize somewhere in between.
And another question for Peter, when you did this analysis of up to, you take the overall diameter constant, right? The total diameter of the up to whatever is the gradient head diameter is constant. Yeah. Is it what constant drives that thing? Like what's the maximum you can go? That's tip speed. You should always be below 0 for open order. Actually, for the previous question, there are probably two cases. Our study is not whether we need 2 motors or 10 motors, but actually it's whether 10 motors or 18 or 20 motors. Because so there are several scenarios. One of the scenarios you have 2 motors, and each of those blades can cover approximately the same amount of area as 10 motors. If that's the case, then the tip speed of those 2 motor scenario becomes critical, because you have very large propeller, and each of them are spinning probably at high RPM. The tip speed is very, very fast. And the other scenario is you probably have two propellers, and each has spin very fast, but at smaller diameter. And those probably can provide the same amount of force as 10 propellers. But in that case, you have very small area, and those will cause high acoustic problems, and because the local flow is very fast, and then there is a shear on the local flow field and the ambient flow. So that's another problem for small number of motors.
I would push back against that, because the military has a wing like this where it's 2 motors, and it does vertical takeoff and it flips this way, and it seems to be working fine for them. So they've probably figured out a lot of the problems that you've talked about for you just using the 2 motors. So then this kind of goes back to the other question: why 10 instead of 2?
I think military, they care less about the fuel consumption and care less about the efficiency.
do something really quiet, with high, because if you go back to the
Military should care about noise. They don't want to create a noise. Like I don't want to land in an enemy and like the airfield.
Well, if you're taking off at a friendly airfield, you don't care if you're loud.
Well, why should I? If I have to land somewhere in a notoriously bad place, why would I make a lot of noise?
I think we're talking about different scales of noise though. If you're talking about the jet engine or
No, this is the propeller.
no, it's the V22. But that's also on gas turbine. It's I think it's turboshaft engine. So they have plenty of power, plenty of everything, right? So I think the same analogy of the turbo fan engine and a high bypass ratio turbo fan engine, small bypass ratio turbo fan. The most advanced or better is the F22 F119 engine, and then for GE90 it's a huge bypass ratio. I think that's probably the same thing because those two, one you care about the performance, you can have tons of thrust, and then you can cruise at Mach 2. The other one you want more high efficiency that way. So in that sense, I think we want more motors for our aircraft.
Correct me if I'm wrong. This Boeing thing or whatever the NASA was trying to do with distributed propulsion, that was completely driven by boundary layer equations. Like you don't want to create a lot of boundary layers, or you didn't want to have a lot of impact on your airflow. That's why they wanted to have a lot of distributed propulsion, and that was the reason they wanted to do multiple motors. Is that same thing valid here? Is there any argument going in that direction, or it doesn't matter?
We do have a considered boundary layer ingestion.
So is that the main thing which drives, okay, I would like to have smaller motors, but a lot of them distributed, rather than having too big like in jet engines?
We are actually studying the efficiency wise, not the boundary layer, but that's one of the driven forces. What we are trying to modeling is actually the efficiency using multiple motors.
Efficiency from where to where?
Efficiency for the motor and propeller pair.
So you are talking about the entire efficiency, electrical to aerodynamic.
system level?
It's from the torque output by the motor and the propulsion provided by the propeller.
Right now, we're looking at just the propeller and motor combination. We haven't started incorporating how it affects the wing behind it. So the distributed propulsion, the propeller itself may not be as efficient because the propellers typically get more efficient as you get larger. So I think what they do is they sacrifice a little bit by squeezing it down. But if you distribute it, your aerodynamics on your wing are a lot better. We haven't incorporated that yet, but that's one of the things that we're
So, but that will be incorporated.
yeah. So right now, what we've done is we've run propeller the same just as like the first go. What actually happens as we start to increase out our motor. The second thing was let's hold the thrust the same and the propeller radius the same and see how the efficiencies change. And the third one is, okay, now if we change the propeller radius and basically run a scan on motor diameters at different propeller radii, how does that affect? And so we're like taking baby steps. So eventually we'll get to how does this actually impact the wing and the boundary layer on that, and what will be like the most efficient.
Sure, but the solution will keep changing as you start
Yeah,
incorporating
as we incorporate
because these are not second order, third order. It's like a
Right.
big changes. In
Yeah. So as we incorporate more into the model, but you kind of want to go one step at a time so you
Sure.
know what you've actually done is correct before moving on to the next step.
Because I'm just almost thinking like why not just a helicopter kind of thing, one big motor and running my big propeller taxes.
So one thing with that is, I mean, it is a lot louder. If you can squeeze down, your propeller is a lot noisier than having smaller ones. And then so it's like there are trade-offs between that. I think the order of noise is important. So I don't know if they have to, like for a military application, if they have to achieve the same low level noise that you would in terms of landing in the city or something like that. It's nice to have, right? But it all depends on whether you want a stealth mission or if you're not really too worried about that or not, right? But yeah, so we're slowly incorporating more into the model.
Okay. Yeah, and one more question, if we have one more. Why do we have to limit the tube speed below sound velocity or sound?
For structural space.
would have shock waves coming off if you go above speed sound. So yeah.
And then what happens?
Really loud.
Everything breaks.
Yeah,
Because some of these supersonic jets, they do fly beyond.
So
sonic
it
waves.
so the jet does, right? But you don't see too many propellers or propeller planes that the propeller itself is actually going at higher than the speed of sound. I think that they created one and it was just a standing shock. So it was like constantly like you just hear the boom coming off of it.
That was actually a problem with the Concorde, and so one of the restrictions was they could not achieve supersonic speed within certain city limits. So they had to be subsonic until they reached cruising altitude, and only then can work. Because at that height, the shock wave doesn't propagate as far. Nobody is affected.
And I'm just curious if there is any way to break this physical barrier.
So
It's like kind of
you might be
limit, right? It's like, okay, I can't go fast.
you might be able to do that with induction fans. But even then, I haven't really seen anybody that was pushing higher speed of sound like that. But that might be one way to kind of get past that. And then you also get, there's noise, but then structural elements, you have to better be able to actually handle.
We should let Michael do his presentation.
Yeah, so it's in there, and then, if you scroll down, I guess, there's a folder called Michael EC 590. Yeah, and then that presentation.
It's always been better to break the physics.
Yeah.
Then it's a science fiction.
We're trying to break their open up correctly. Yep, look good. And let's click on that.
Yeah. Okay. Am I good to go whenever? Okay. Hi everyone, my name is Michael Wu. I'm doing research with Professor Banerjee right now. And today I'm going to present kind of my work on my research, which is developing a real-time health monitoring framework for IGBTs. Before I started, I just wanted to give a couple of acknowledgments. I wanted to thank Chi-Chen, who's another member in Professor Banerjee's research group, who I'm working alongside with in this project. And then I also wanted to thank a couple of people from Professor Nenad Milkovich's team in the mechanical engineering department, Johannes and Nithin, who are working on the mechanical and thermal side of things. So the main question is, why is real-time IGBT health monitoring important? And so, recently IGBTs have become very popular because they combine certain gating characteristics and also the current density characteristics of MOSFETs and BJTs. And so they're used in a lot of higher power applications because of that. And if we look at this pie chart here on the right side, we can see this is a pie chart that was a result of a survey on the different failure rates of components in power converter systems. And as we can see, semiconductors right here represent a pretty significant portion of these failures. And so, in these locomotive systems, which is kind of the problem that we were introduced with, in a locomotive system, how can we monitor the health of these IGBT power modules? In these locomotive systems, if one of these IGBT modules fails, the results can have pretty severe implications. It can result in a lot of damage in whatever these locomotives may be carrying, whether it's passengers or cargo, whatever it may be. So our goal is then to develop a health monitoring framework that is able to monitor the health of these IGBTs during operation of these locomotives, which is important so that, as these trains are operating, we can detect if anything might be going wrong, and we can also predict how much remaining lifetime is in one of these power modules. One of the things that we're also doing as part of this project is we are developing sort of a fault identification board, which in case of a fault, let's say when the DC link voltage exceeds a certain limit, or when the current going through one of these IGBTs also exceeds a certain limit, this data storage board will store all of the measurement data so that it can be analyzed later. And this needs to be separated far, far away from the IGBT power module in case of some sort of failure. So what causes, if we have two different materials, each of these with different coefficients of thermal expansion, here denoted by alpha, we can see that if they undergo some sort of temperature change, they'll undergo different amounts of thermal expansion. So as you can see right now, as these materials are not connected, it's totally fine if they expand different amounts. However, when these materials are bonded together, when they undergo some sort of change in temperature, then that's where we get some thermal mechanical stress in the system. And so typically, inside an IGBT module, you'll find a stack of a lot of different kinds of materials, whether it be the IGBT chip itself, which is silicon, different connectors or plates, which are, even the insulating substrate, which are all different kinds of materials. As this IGBT module undergoes a lot of power cycling, temperatures, while it's dissipating power, temperatures will increase, and while it's not dissipating as much power, temperatures will decrease. And so this thermal cycling will introduce a lot of stress in the system. There are typically a few different kind of failure modes. One of them is these bond wire liftoffs. So the bond wire will make a connection, is made out of some sort of conductor, and then it's bonded to the silicon chip. And so because of this, there are two different materials, once it undergoes some sort of thermal cycling, then these materials will expand different amounts, which will cause thermal mechanical stress. And over here on the right side, you can see there's a scanning electron microscope image of what a lifted bond wire might look like. Is a solder joint that goes in between the chip and the copper plate below it. And so over time, through thermal cycling, you can see that this solder joint becomes delaminated over time. And also, there's another solder joint that connects the connectors to the IGBT module. And over time, the solder joint will also become stressed. So in fact, we can actually find out how many different kinds of these sorts of stresses the IGBT module can endure, and that's represented here by big N. We can see that it's a function typically of changes of temperature, max temperature, and also the number of cycles that we're going through. And so if we look at this equation down below, this is where here we have big N representing the number of these different thermal cycles that the IGBT module can undergo, and little n here representing the number of cycles that the IGBT module has undergone so far. If we sum them up together, we get a total representation of damage, which is a sort of fraction. And as this fraction gets closer and closer to 1, then we know that it's some sort of failure state. And this rule is called Miner's rule. So we can see, one last thing to mention before here. The way we calculate or we find the little n is by looking at a junction temperature profile. And from there, using a rainflow counting algorithm, then we can determine how many what kinds of these power cycles we've gone through. So then it's crucial then to be able to estimate junction temperature. And so there are a number of different methods that we can do this by. On the left, we can see a couple of methods that are not feasible in our health monitoring frame. Would require us to physically drill into the IGBT power module and directly measure the junction temperature, which is not really feasible during real operation. Other ways we can do this are by measuring on-state voltage, which is the voltage across the collector and emitter of the IGBT, with low current, which is not really feasible again in our situation because while we're operating this IGBT module in a locomotive, current levels are going to be really high. And also we can measure the gate threshold voltage, but again, this is not something that we can really do during operation. There is one method that is more feasible for real-time implementation where we can measure on-state voltage with high current, but the ohmic voltage drops. As you have a lot of currents, you will introduce a lot of inaccuracies due to ohmic voltage drops. So our current method of then estimating junction temperature is to use a thermal model. And the way that we're modeling our IGBT module as a whole is by observing how certain power pulses or power dissipation pulses affect the temperature of the system as a whole. So if we take a look, we just assume we have some sort of DC, or we have some sort of constant power loss pulse for some period of time. We can see that it affects temperature in this sort of a fashion. And so For example, this is some power loss pulses that we've calculated based on some data that the company has given us. So we can see, we have power loss pulses that from basically the switching on events, the conduction events, and the switching off events. And if we represent these as a superposition of pulses, where we basically have a positive component and a negative component that cancels out the same pulse, we can see here that we get, we can kind of plot these different temperature effects on the same axis, and it looks a little bit something like this. So you can see when we have P1 here, it affects the temperature at time equals 0, and then when we have conduction here, P2, we have another temperature profile that looks a little bit something like this. Now, when we add all of these together, for example, this left plot is the plot that we just saw on the previous slide. But if we add up together these contributions from one of these power loss pulses, we get something that looks a little bit like this. Now, if we sum all of these together, then we get something that looks like this. And we can see that this then is basically how our junction to case temperature will look like over the course of operation. And so this means that we don't need to have a temperature sensor that just measures junction temperature. Instead, now we can have a temperature sensor that's mounted somewhere on the case. It measures the temperature on the case rather than at the junction directly. And all that needs to happen then is we need to model the thermal path from the junction to the case to that point, and that will give us our thermal model. Now then, it becomes important to be able to accurately calculate power loss. And so in an IGBT module, there are typically 4 components of power loss. There are 2 components of IGBT power loss, which is conduction power loss and switching loss. And conduction loss is calculated just by taking the on-state voltage multiplied by the current going through the IGBT. And switching loss is then calculated by the switching frequency times the energy that it takes to turn the IGBT on and the off energy as well. And then in the diode, there's also conduction loss, which is the diode forward voltage times the current going through the diode, and also reverse recovery loss, which is the loss incurred when the diode goes from a conducting state to a blocking state. So as you can see here then, it's important if we wanted to calculate switching loss and reverse recovery loss, we would need to take a look at these energies, which would require us to observe the transients and be able to sample and integrate them. However, these transients are really, really short. And in the datasheet for the IGBT module, that it's actually spec'd at around 400 nanoseconds. And so we simply don't have enough sampling bandwidth to be able to calculate these energies. So what's our solution to this problem? Instead, we decide to use lookup tables that are provided by the manufacturer. And so this gives us basically characteristics of the switching energies and the reverse recovery energies at different operating points. So as you can see, switching transients are too quick to be sampled and integrated. So in order we have to use these lookup tables, and we can see that these energies are given in terms of blocking voltage, which is your DC link voltage, the current going through the module at the period of time, and also the junction temperature. Also, then we can calculate conduction loss by just by measuring the collector emitter drop and also observing the current going through the module. So then our challenge comes with, if we want to, seeing that we're using lookup tables to calculate our transient losses, then how can we calculate conduction losses? And our main challenge then is how can we accurately measure the collector to emitter voltage? The challenge with this is that the measurement circuitry needs to withstand our high DC link voltage while still measuring our on-state voltage with high precision. In our case, our DC link voltage can go all the way up to 3 kilovolts, but our collector emitter saturation drop across our IGBT will typically be around 3.5 volts. So also our measurement circuitry must provide enough isolation to protect our digital components. So how do we solve that problem? Our first measurement topology looked a little bit something like this. We connect our collector and emitter to our circuit, and it goes basically across a resistor divider. And this voltage then across a resistor divider gets fed into an instrumentation amplifier. Now because this collector and emitter can go up to a really high voltage, our resistor divider needs to divide this voltage down to fit within the input range of our instrumentation amplifier. However, an input instrumentation amplifier is chosen because this amplifier also has a characteristic of having internal gain. So whatever we divide the voltage down by, we can also gain it back up internally. And we can use this input instrumentation amplifier to basically clamp our output voltage that goes to the rest of our measurement circuitry. So this means that we have a 3 kilovolt maybe DC link voltage, but as that gets divided down and gained back up, at the end it just saturates our instrumentation amplifier, and it gets clamped to the supply voltage of this amplifier. Now this output goes to a monostable multivibrator, which on the falling edge will send out a pulse and will close this switch. And this switch will then charge up, as the switch is closed, then it will charge up this capacitor, which is connected to the input of an isolation amplifier, which will then go to our microcontroller, which is doing all of the sampling. Now, basically, you can see here on the right, this is what the sampling basically will look like. We can see that our collector emitter voltage will go from pretty high. This is our DC link voltage to its saturation voltage, which is around 3.5 volts. And this is the pulse that's being generated by our monostable multivibrator. So as soon as this pulse ends, then this capacitor is charged, then we signal to our microcontroller that it's OK to sample. And then we will grab a sample here at the saturation voltage. So in the case of a three-phase inverter, these are basically the analog measurement points that we have. We connect across the collector and emitter of each of these IGBTs on both the high side and the low side. And in our case, we have Hall effect sensors that are measuring the current going into our motor. And we will also be measuring DC link voltage, which is an input parameter to some of our lookup tables. Okay, it looks like part of this image is missing, which is a little bit weird. But this is, I guess, a partial picture of our hardware setup. Here we had a three-phase inverter here. And this three-phase inverter uses IGBT modules, and we've tapped off connections that feed into a resistor divider. And then underneath here is our three-phase inductor, but we're only testing with one phase at the moment. And this is our Hall effect current sensor. This here is a picture of our measurement board, our microcontroller, and this is our data storage board. So we've conducted hardware testing so far using a pretty low DC link voltage, about 50 volts, which means that our resistor divider ratio doesn't have to be so high. In our case, we've only designed it to be 5:1. And these are some experimental waveforms. So as you can see, the yellow waveform here in this case is our VCE. So this is measured directly across our IGBT. And so with our 50 link DC voltage, we can see that the IGBT is switching from 50 volts to something that's a little bit above 0 in our case. And this green waveform is then the output of our input instrumentation amplifier. And we can see that it successfully clamps this input voltage, albeit with a little bit of delay. As we zoom into the bottom portion of this waveform, we can see that, that the instrumentation amplifier output actually follows the collector emitter voltage pretty well near the bottom, which is exactly what we want. And there's a little bit of error, which can kind of be chalked up to just internal gain errors and also errors in the resistor divider. And this is the voltage across that capacitor that we're using to sample and hold the voltage. So as you can see, yellow waveform again is our collector emitter voltage that's measured directly across our IGBT. And then our green is our capacitor voltage. You can see that there's a little bit of instability when our switch closes and the capacitor begins charging. But in general, as we sample, which is about right here, which is about 40 microseconds after the falling edge, we're able to effectively track the collector emitter saturation voltage, which is what our microcontroller is sampling. Now, there are a few weaknesses that we've identified through hardware testing of this current measurement topology, which is why we're looking into certain other circuits at the moment. One of the issues is when the divider ratio is large, as we can imagine, if we have a 3 kilovolt DC link voltage and we have to divide it within the input range of our instrumentation amplifier, which is much, much smaller. When the divider ratio is large, then our 3-volt signal gets divided by that same divider ratio. And it's very easy then for noise to kind of corrupt this voltage, which will then make our measurements at our microcontroller very noisy. And if we're not able to correctly measure collector emitter saturation voltage, then that affects our conduction power loss, which will then affect our thermal model. Also, if the resistor values are selected to be too large, then the resistor divider, then we begin seeing a lot of imperfections in the voltage across each of these individual resistors, which is something that we were seeing in hardware. When we were using our 50 volt DC link voltage, and we're using resistors in our divider that are about 1 mega ohm each, we were seeing that the voltages across each of our resistors were not exactly square. And in fact, there were a lot of weird artifacts going on in these waveforms. And so these resistors need to be sized properly. One, that they can handle the amount of power that they need to dissipate, but also two, that they still allow the voltage across them to be perfectly divided. So because of those weaknesses, we are currently investigating a different circuit topology, which is a different method of then kind of clamping that voltage and making it safe to input into our measurement amplifier. And so in this case, we're placing a Zener diode and a and a normal diode in parallel with our IGBT module. And so in this case then, we also have a resistor here, and these resistors then limit the current going through your Zener diode and your diode. So we can see here there are two different cases for each of these IGBTs. When the IGBT is off, the switch is effectively open. We have the DC link voltage across both the Zener diode, and we have the DC link voltage across these two nodes. So then this reverse biases the Zener, so the Zener breaks down, and then also it forward biases this diode. And so then the voltage across this node then, which feeds into our amplifier, will be basically the Zener's reverse voltage plus the diode's forward voltage, which will be safe to input into our amplifier. And then when the IGBT is on, then the voltage across the IGBT will be its saturation voltage, which will typically be around 3.5 volts. And that 3.5 volts will not be enough to break down this Zener diode, which means that it'll basically be an open circuit, so we'll be able to see the saturation voltage directly at the input of this amplifier. Different design decisions we need to make, though, is that this resistor is limiting the amount of current that's flowing through these two diodes. But at the same time, this resistor value cannot be too big, because we basically do not want this resistance to overpower basically the resistance of this path when the voltage is low, because then we wouldn't see the entire collector-emitter saturation voltage across the input of our amplifier, as it forms its own sort of impedance divider. So future work in this project involves investigating the effects of humidity and vibration on the health and remaining lifetime of these IGBT power modules. And also, in parallel with the hardware that we're working on right now, we're also developing fault detection and data storage system and software using an FPGA. And then in the meantime, also, we are working on constructing the circuit that I just went over, and we hope to have test results on that soon. So, thank you. Yeah.
Does do like the trends that you saw for the temperature distribution, would that change as the health of your IGBT? Like, so does an unhealthy IGBT have the same like reaction to a power pulse than a brand new one? Or
that's actually a good question. I think that's kind of beyond the scope of my knowledge. That's something that the mechanical engineering team is working on. Yeah.
Can you use this monitoring system for MOSFETs or semiconductors?
I think if you're concerned with maybe the drain to source voltage of a MOSFET, it might be possible. But I know that in other kinds of transistors, there are also maybe other indicators that work better as indicators of health health. Like I know in the case of a MOSFET, you may be looking at leakage current into the gate, etc. Yeah.
Kind of following on the question you asked. I don't know how much of the mathematical modeling of the failure that you're looking into, but have you considered sort of like doing Markov models for reliability? Because the propensity for you to move from one state to another, so one failure state to another failure state, kind of depends on the current failure state that you are in. So, moving from one step to another depends on your current state in some sense.
Sure.
So I was just curious if you guys if that's something that you are thinking of.
No, that's something we haven't looked into yet. Yeah.
And the other question I had was, can you go back to the I know, for instance, silicon carbide devices, manufacturers derate their devices, so the data sheet that you actually receive does not necessarily reflect the true characteristics of the device.
Okay.
Because of various reasons of defects in manufacturing. Is that something that is also likely to happen in information that manufacturers provide for IGBTs? And if so, will you essentially end up identifying a failure of a device sooner than it is likely to happen?
That's a pretty good question. I would say in the lookup tables that we're using right now, probably not, because I think that what these lookup tables give us are kind of the energies during these switching transients, and they just give us basically they give us a way to look up just how much energy it takes to kind of turn on and off these IGBTs. Not necessarily, I guess, anything particularly safety related, and we're using these then to kind of go into our. I guess we're just using these measurements then to go into our thermal model. So I think that the data that we're taking from the manufacturer is not directly safety related. So I don't think I'm too concerned about that. Yeah. Oh, okay.